So we're back to section 2.7 again, and this time example 2, calculating horizontal asymptote. The difference here is that for this function we'll see very soon that it's not infinity over infinity anymore. It's another basically, to find the horizontal asymptote, we will have another indeterminate form. And so the first thing that comes to mind, let's calculate the limit as x goes to positive infinity of this. What will happen? Okay, in this case, you can see that if I plug in infinity, positive infinity, I get infinity minus infinity. So the form of this one is infinity minus infinity and requires some clarification or simplification, something to figure it out. So these type of these are, as well as the other problem, example 1 problem, are very typical for calculus 1, and so what you want to do is to learn the technique to take care of this. And so what is the technique? The technique is to multiply top if it's indeterminate form. If it's not indeterminate form, just leave it that way. But if it's indeterminate form, basically multiply by the conjugate. And this is indeterminate form, so I'm multiplying that by the conjugate. And conjugate of that is just x 4x to the second plus x plus 2x. And divide by that conjugate. 4x squared plus x plus 2x. And if you multiply the top, you will end up with 4x squared plus x minus 2x to the power 2, which is 4x squared. And the denominator stays and the same. So now you clean it up and we end up with x over square root of 4x squared plus x plus 2x. Now we're back to that quotient function that we saw in the previous questions. And so now I have to factor out. And so in this case, factoring it out. Now top is completely factored. Factoring out x squared, and it comes out of the function as absolute value of x. And you get 4, I'm skipping one step, and 1 over x. And this one becomes, again, 2x. Okay, so I skipped one step of, I just factored and brought out. But over here, do you see that here is absolute value of x, that one is 2x. But in this specific case, because x goes to positive infinity, that is going to be just x. So I can factor x over x times square root of 4 plus 1 over x plus 2. And these two simplify. And so you have to find this limit. If I bring the limit in, if I bring the limit in, it's 1 over square root of 4 plus limit x goes to infinity of 1 over x plus limit of 2 is 2, and so we end up at 1 over 4. So y equal to 1 over 4, is one of the horizontal asymptotes. The other part to notice is that this function doesn't have any other horizontal asymptotes. As limit as x approaches negative infinity, this is of the form infinity because it's infinity minus infinity is positive infinity. And so this part I don't have to calculate. The only one that we needed to calculate was the this limit which was of the form infinity minus infinity, and we calculated that this side of the limit gives you 1/4. Let's compute the second limit, and so here if I limit x goes to positive infinity of this function, then I should factor out an 8, x to the power 8, and end up with 1 over x to the power 5 minus 2. As x goes to positive infinity, if I bring the limits inside, this part goes to -2 because that part, the limits, this limit is equal to -2, and so it will be -2 times positive infinity, which is a negative value. So this limit gives me a negative infinity. Now how about the if it goes, so I'm going to show this with a negative value here. So infinity, and we did the positive one. Now let's do if it's negative, what will happen? So if it's negative, then we have to do this one too. And so if it's negative, then x to the power 8 is still going to be x to the power 8 is still a positive value, and multiplied by negative, it's going to be a negative infinity. So let's do example 2, part 3. This time is h of x equal to arctan of e to the power x. And the function is, again, another, we had the composition in this section of functions that were square root or polynomials and so on and so forth. But we haven't had an arctan in e to the power x and all of that mixed together. So one thing to remember is that I need to know how the inner function is reacting to figure out how the outer function, the limit of outer function is. So since I'm computing two limits, I'm computing limit as x goes to infinity of arctan e to the power x, and also computing limit as x goes to negative infinity of arctan e to the power x, I need to know what is the limit as x goes to infinity for e to the power x, and limit as x goes to negative infinity. How do I figure that out? I go back to the picture of it that I remember. It looks like that. So y equal to e to the x looks like this. And if you know this as x goes to negative infinity, so limit e to the x, x goes to negative infinity is equal to 0. Limit e to the x, x goes to positive infinity is going to infinity. So the next step that I want to do is basically to replace the inner function by a variable u. What is u? U is e to the power x, and I know if x goes to infinity, u goes to infinity as well, and over here as well, right? And so what I do is I simplify this. In here, u also goes to infinity. So I'm doing both sides at the same time. so you can compare them together. In this case, limit as u goes to 0, because as x goes to negative infinity, u in here goes to 0. Now, what I know is arctan is defined at u equal to 0, and so I just have to plug that in. That's the direct substitution. So it's arctan of 0, which is equal to 0. But if u goes to infinity, I don't know, I mean, I cannot do the direct substitution. But also, I know arctan function looks like this. Here's pi half, here's negative pi half. So I know that the arctan function, sorry, I should have dotted that one. So I know the arctan function as u goes to positive infinity is basically the end behavior. It is going to be pi half, because arctan has the pi half and negative pi half as horizontal asymptote. So I get y equal to pi half and y equal to 0 are the horizontal asymptote of this function. So let's do one applied example. Example 3, calculating horizontal asymptotes. In the interesting part of it is just that you get some idea about what horizontal asymptote means for us in real life also. So a tank contains 100 liters of pure water, brine, and that contains 30 grams of salt per liter of water is pumped into the tank at the rate 25 liters per minute, and will mix solution exit at the same rate. What happens to the concentration of salt as time t approaches infinity? Okay, so let's think about this. This is the container, and water comes in at whatever rate, 25 liters per minute. And the interesting part is that in your future courses, in a little higher calculus courses, you have to, or differential equations, you have to actually calculate this model entirely. We're just looking at the horizontal asymptote for the model, but the other courses you have to compute this completely. And so and there's 100 liters in here, and then the water in here has 30 grams per liter, and sorry, the water in there has 0 grams per liter, 0 grams per liter. And the brine has 30 grams of salt per liter is coming in. 30 is coming in. 30 grams per liter. And so as time passes by, and so we'll mix the solution exit with the same rate, 25 liters per minute. It seems like the new water comes in with the salty water comes in, mixing with the water that is already there, and then exits, right? And so it eventually all the water in there are gonna, as time goes to infinity, all the water is going to be washed out. So what all the water that was already in there going to wash out, be replaced by this one. So what is happening is that the concentration of inside as limits of the concentration C of t as t goes to infinity has to be the concentration of what is coming in, 30 grams per liter. This also gives us a little bit of insight on what the model looks like. If this is C of t and this is t, I know that, and this is 30 grams per minute. So a little review of what we've covered so far. For finite limiting values, we have 4 algebraic techniques so far. There's a direct substitution, requires continuity, and it has to be a determinate form. And we have the simplification for indeterminate forms. We have a simplification and conjugation and the squeeze theorem. For infinite limiting values, we have 2 techniques, manipulation involving limit as x goes to plus minus infinity of 1 over x to the n equal to 0, and then horizontal asymptote of common functions, e to the power x, natural log of x, and arctangent of x. So every time we had to go back to those basically the graphs of the function to remember how the infinities react with them. And so limit is really the heart of the calculus sequence, and it's going to be used multiple times throughout the course, this course and follow-up courses in calculus. And so there are, in Math 125, there are 2 more sections that are devoted to limits, section 2.6 and 6/3.6 and section 4.5, in which evaluates limits with indeterminate forms. So these are the sections that we use to compute limits, and there are multiple sections that we use limits to compute other things. And so again, these are the ones that these are the techniques that we discuss here. You will see them over here, but also you will see limits throughout all sections and follow-up courses.